So let's get started with work power energy topic. Okay, see, when we in this particular chapter, one of the most important thing is calculation of work done. Major part of chapter is understanding work done, how to calculate work done. If we understand work done, then our work is done in this chapter. So one way of thinking of what is work done and why it is so important. The work done, see, we basically we understand that overall energy is conserved. So energy keep changing different forms, and the way the science work, we keep converting energy into a useful form from particular source of energy. So what is work done? And kinetic energy is important for us. See, if kinetic energy was not there, practically every device works on some form of kinetic energy. And how do we impart kinetic energy, and how do we make object lose kinetic energy? So whenever change in kinetic energy happens, it has to happen only through a means of work done. The work done is a means to convert some form of energy into kinetic energy. So that's the work done. Work done, we are talking about physics sense work done. Physics work, so whenever work is done on an object, then only kinetic energy change, or other way around also is true. If kinetic energy changes, it means work must have been done. And if we apply our understanding from previous two topics of kinematics and laws of motion, very easily can understand we know, say velocity will change from value of u only if there's an acceleration. And if there's acceleration, there has to be force. So force and displacement are necessary for change in kinetic energy. But sometimes when the force is existing, displacement, still there's no change in kinetic energy. So we understand here. So see, if you try and understand how does kinetic energy changes, think of something like this merry-go-round. And a child is standing here, and assume that this part is, and whenever this merry-go-round, you can apply force on merry-go-round in different direction. And depending on which direction you apply your force, the kinetic energy will change. And if you something like this, suppose you stand here and keep pushing the merry-go-round in the radial direction, the displacement will not take place, kinetic energy also will not change. The other thing what we notice, there must be some displacement with the force. But even sometimes when there's a displacement, suppose this merry-go-round is rotating, and you also keep running around the merry-go-round, and you keep applying a force which is always directed towards the axis of rotation. You're applying the force, you're moving around the merry-go-round, still you find the kinetic energy does not change. Another way you can think of, suppose you keep a rod, a light rod in a horizontal plane, and there's a hinge here, just like a door kind of hinge. So this rod is free to rotate in this horizontal plane, and this mass is attached here. Now, if this mass also, we can apply force like this, we can apply force like this, we can apply force like this. And very easily, intuitively also we understand here, depending on which direction we apply the force, it will have different kind of motion. It will gain different rate at which kinetic energy will change will differ. So we understand here. So basically, imagine one, you can also understand this one. So centripetal force. So whenever force is like this, we apply force like this, and it is still rotating. Somehow we make it rotate and then keep applying force, which is always towards radial direction. What if the kinetic energy will not change? Why is kinetic not changing? The work done depends on vector quantities. Force and displacement, both are vector quantity. But when both are there, product of the two is in a third quantity. Product of, see, they can have different kind of product, different type of result. So if we have product of force and displacement, the result is work done, third physical quantity, which is scalar. And hence, if you recall the principle of vectors also, when we multiply two physical quantities, which are vectors, the result could be a scalar or a vector. If it is a scalar quantity, it's a dot product. So work done being a scalar is a dot product. And the way the kinetic energy acts also, it is consistent with the dot product. So a very simple way to this a point of application. For a small displacement, what he has seen, the magnitude of force has not changed, direction has not changed. So typically we assume for a small displacement, force can be taken as constant. So if this angle is theta here, Even after a small displacement, this angle remains theta, and this is a force acting. And so what is work done? Of course, one way we can think of a dot product, but I think we can think of other way also, which makes more sense. What is other way? These are the two quantities, and dot product is F magnitude of force into magnitude of displacement into cos of angle between the two. Now this cos theta I can attach to force or I can attach to displacement. If I write F cos theta into dr, we are writing all scalar quantity. These are all magnitudes of force and displacement. If I write like this, what is this one? This is component of force along displacement. So one way of thinking work done is I can resolve the forces into two components, one along the displacement and one perpendicular. So which is the one which is doing what? The component of force along displacement into displacement, magnitudes. Or we can attach this cos theta to dr term. It can also be written as F into dr cos theta. So what is dr cos theta? This is component of displacement. So either I can take component of force along the displacement, or I can take component of displacement along the direction of force and multiply by magnitude of force. So that's how we can arrive at different ways you can calculate work done, which is fairly simple. Now, if a force is constant, then it can be written as a dot product of force and displacement, delta R. And in that case, if force is constant, it becomes delta R. It becomes independent of path. So let's understand what does independent of path mean with some example. Just imagine here, there are three cases given. This is mass M attached here. And these are two horizontal planes, and distance between two horizontal plane is h. It means upper surface is at a height h compared to lower surface. And there's a hinge here, the length of the hinge is also h. So what happens if we attach a mass here and release it? Of course, the mass will swing back, and when it reaches the lowest point here, it will have a particular speed v1. Okay. Second case, we do same mass, we place it here. We place it on a smooth surface, and it has an angle theta here. So in this case, it had a different path, and as it moves at different point, it will have a different acceleration, which is difficult to calculate. So if you have to actually calculate velocity, it becomes a little complex using kinematics method. But if we take this case, if surface is smooth, you can easily calculate its acceleration, and it reaches the bottom at certain speed v2. It will have kinetic energy corresponding to 1 by 2 and v2 square. Third case is something like this kind of thing, what is slides, what you see in Ocean Park and all. So here it is kept on a smooth surface, and here also it undergoes different acceleration, and it has velocity v3. So all these cases, what has happened here, when it reaches here, experimentally we can find, and theoretically also what we find, the magnitude of velocity when it reaches the bottom is same in all three cases, or it reaches with the same kinetic energy. So how do you understand why is the kinetic energy same? So in this case also we start thinking, why is the kinetic energy, first of all, why is the kinetic energy changing? Because work is being done. Which forces are doing work here? Two forces are present. One force is of course tension force here. And here that other force is normal reaction. Here also there's normal reaction which keep changing direction. So there are two forces present. One is constant force, other is varying force. But work done by tension or the normal reaction is zero because the displacement is always perpendicular. So here work is being done by gravitational force, which is constant. So I can think of what is work done. Work done is equal to the force multiplied by component of displacement along force. So here also this is a displacement. So first of all, the path is like this, but still I can take, if the force is constant, it is equivalent to this path here. And what is the vertical component of displacement? Vertical component is h. So all three cases, this also we can understand. The 2 points we can understand here. If force is constant, whichever path I have taken to move from initial point to final point, work done remains same by constant force, and also smooth reaches same. And the second thing we can also understand here, we can always take work done is also equal to force multiplied by component of displacement along force. Okay, so it's a little bit of understanding work done. Otherwise, it should be fairly simple. We'll look at few more examples of calculation of work done. But in some cases, it's a dot product. So it is also possible to write both this vector quantities in terms of unit vectors. If we write in terms of unit vector, and if force is not constant, the dot product is scalar quantity. If it is scalar quantity, we can add it up just like an ordinary arithmetical addition. So we can directly integrate. So if this we integrate over all small displacement, so this is the work done over a small displacement dr. Dr means, see, whenever you have small displacement, any small displacement, if we have a small displacement dr, it will have certain component along x direction, certain component along y direction, certain component along z direction, and relative value of dx, dy, and dz will depend on orientation of displacement. It will depend on its path. So this is something dr we have just written is component form, and we dot product we take here. So what does this indicate? This indicates work done by a variable force, which is a function of r, as the part from where to where initial point is r1, final point is r2. Here also we can integrate. We'll come to some example. So there are two kind of cases. Work force is constant, and force is a work function of position. So in that case, both we can calculate. And one important application of work done, as we said in the beginning, work done results in change in kinetic energy. So change in what is work energy theorem? If number of forces, and we talk about here, we are talking about translation only. So translation, whatever may be the shape of object, if it undergoes translation, I think we had dealt with earlier. So if object undergoes translation, so forces may be acting at different points. But if it undergoes translation, all points will have same displacement. So I can replace the object of any shape with the equivalent point object. So even if it is an object of different shape, it could still be treated as if all the forces are acting at a point, because full object can be represented as a point object. Now, when we talk about, so when multiple forces act here, and so work done by all forces, if I calculate, it will be equal to change in kinetic energy. That's work energy theorem. This is what we need to keep in mind. So if there are multiple forces, F1, F2, and F3, there are two ways of calculating work done by all forces. What are the two ways of calculating work done by all forces? One way of calculating work done all forces, I calculate the resultant of all forces. The work done by all forces are also equal to resultant force into displacement. So it can be work done by resultant. That's one way. Or we can calculate work done by each force separately and add it up. So what we have done here, so you see, all forces are not same. We categorize work done by all forces into two categories. Some of the forces, by definition, I will not go into too much of this. I hope we all understand what does conservative force mean, what is non-conservative force. So we divided work into two parts. One is all work done by conservative force plus work done by non-conservative force. Same thing we written, just broken it up into two parts. Now, when we talk about what is change in potential energy, change in potential energy is equal to negative of work done by conservative force. And why negative? Let's have an intuitive understanding of why negative. So let's look at this also. If object is falling, object is falling, it as it falls certain distance, its kinetic energy increases. Its kinetic energy is increasing. But if you say the total energy is constant, if something is increasing, there has to be corresponding decrease in something else, some other form of energy. So if K increases, if total energy has to remain constant, there's some other form of energy which is associated with position. That energy must decrease. That energy we call as potential energy. Potential energy is related only to conservative force. Now, when we talk about kinetic energy is increasing, what is kinetic energy? Kinetic energy is equal to work done by conservative force. If U is opposite of kinetic energy, automatically U becomes negative of work done by conservative force. So why negative? Because K and U are opposite of each other. Directly it comes from there. So what is minus du? That is what you need to keep in mind. Change in potential energy is equal to negative of work done by conservative force. Okay. So in this case, what we have done here, where this conservative force, I have replaced this minus delta U. This is this from here. So when we replace work done by, this remains same. So work done by non-conservative force is this expression. We take it to other side. So work done by non-conservative force on a system is equal to change in potential energy plus change in kinetic energy. So when we use this equation, I will not calculate work done by conservative forces. I'll calculate only work done by non-conservative forces. And due to conservative forces, I'll just calculate what is the change in potential energy, and which many cases we know simply. And one of the gravity is pretty simple, and spring also is fairly simple. So let's understand what is potential energy stored in a spring. So whenever we talk about a spring, again we go to basic characteristics of the spring. It has a natural length and has a spring constant K. And why string constant? Let's say the one side it is fixed to a wall. There's something like a wall, and here also attach some object here so that I can apply forces. What we have done here, see in this case also, we have taken x is equal to 0. So when we talk about, we write and we use expression as spring force equal to minus kx. What does x indicate here? See, in this case, what we have taken, one end is fixed, and only we're assuming one end is in motion. We can always keep this point as fixed. We can attach it to one end of the spring. Other end, when it is natural length, I take its position as x is equal to 0. We have taken x-axis along the length of the spring. Now, let's see. So this is the state here. And let's see, we slowly start applying a force. Very slowly we apply a force and gradually keep increasing. So we are increasing the force in very small increment, 0.1, 0.2, or maybe even 0.01 Newton, 0.02, 0.03. As we gradually keep increasing the force, what will happen? The spring also is, as we apply greater and greater force, it will have more and more elongation. The position of quasi-equilibrium also will keep shifting. Let's say here, as the spring also elongate, and as we double the force, elongation also becomes double. That indicates the elongation of spring is proportional to external force applied. And since it is in equilibrium, why it is in the state of equilibrium, if it is in equilibrium, whatever external force we applied here, spring is applying equal and opposite force. So what is happening as we are gradually increasing F, X is increasing and spring force also is increasing in the same proportion. If elongation, this direction spring force will act, and spring force net force has to be 0. Spring elongated is pulling both the surfaces in. So when you elongate the spring, it is trying to come back to original shape by pulling at this end and pulling at this end. And more you stretch, accordingly, pulling force also will increase. So that's what you understand. How do we, in this case, taking this as sign convention, displacement x is positive, and spring force, we are writing spring force at the displacement x. This is spring force. Spring force is acting opposite to direction displacement minus kx. Now let's understand here. This is x here. Now from here we give a very small displacement dx. Further small displacement dx. When we give very small displacement, there will be work done by external force and there will be work done by the spring force. And we notice here work done by external force will be positive and work done by spring force will be negative, and both will be opposite to each other. So if we mark this spring force, see what happens in the spring force. If I have to plot spring force on the y direction, it's a function of displacement from the mean position. This is x position, and this how spring force will vary. Fx is equal to minus kx. The slope will be negative, and this is how the spring force is when it is a position x. This is Fx, the spring force, and I stretch it by a small distance. If I stretch it, it will work done by spring force will be equal to Fs into dx. What is Fs into dx? Fs into dx is nothing but area of this small rectangle which forms. So Fx into dx is area under force displacement curve. We should have understood anyway. So y dx, what is area under y curve and x-axis? Y dx, here area under the curve will be Fs into dx, and this term is a third physical quantity called work done. So area under this curve indicates work done. If I take any two corresponding point, it will give me work done. Okay, so work done by a stretch from x to x2, area under the curve. So this is positive work done by the external force, but work done by spring force is negative. But if work done by spring force is negative, change in potential energy will be positive. So if I want to calculate what is the change in potential energy here, this is the change in potential energy as it changes from x to x plus dx. So if I mark this point here, what would this area indicate here? This area will indicate work done in stretching the spring from 0 to x. And this work done is negative, and this area is equal to this coordinate. This is the area. This is ux. Negative of work done is the potential energy here. As x keeps increasing, area keeps increasing, corresponding the ordinate increases. So any point, what is the ordinate indicates here? Ordinate indicates area under fx curve up to that point. That's a simple understanding of mathematical relationship between potential energy and work done by conservative force. And easily we can notice here, even in this case also, it will become a similar way. So this will be the shape of potential energy curve, and it will vary as, yeah, so we can calculate term fx dx. Other thing what we notice here, work done by external force, slow stretching force. So du will equal to minus f into fs into dx. But since external force is equal and opposite, change in potential energy can also be written as work done by external force if external force is acting on the object very slowly, so that it is always almost an equal and opposite to conservative force. There are two ways of understanding change in potential energy. Change in potential energy is equal to negative work done by conservative force. It is also equal to work done by external force in moving the object slowly, so that there is no change in kinetic energy, and these two forces are equal and opposite. Okay, that's what you need to understand here. Now let's come back to its application. In terms of theory, it's really not much. Very simple. It's a dot product between. So that's all the theory is. What is work done? Dot product of force and displacement. And that is equal to change in kinetic energy. And then we divide work into two parts, conservative, non-conservative. Work done by conservative force is equal to negative, change in kinetic energy, change in potential energy equal to negative of work done by conservative force. That's all theory is. Rest all is application. Now let's look at some questions here. A block of mass m is lowered with the help of rho of negligible mass through a distance d with an acceleration of g by 3. This can happen in the lift also. As soon as you get in the lift, when this lift is moving downwards, if you get on the 14th floor, you are going down. Of course, the lift will have a downward acceleration, and the rope will apply some force. Okay. So just so whenever questions are given, it's a question change of, since the acceleration is constant, it's a question on constant force. So whenever we have to calculate work done, so initially when we do some simpler question, practice with mark displacement of the point of application force and force also, direction of force, for which work done has to be calculated. So either we visualize what is happening, or we draw a simple figure of what is happening. If we draw initially simple figure, later on perhaps we can just visualize and draw. So this is what it is. This is something, this mass m, and there's a tension force acting here. It is having downward acceleration. It has moved through a distance d. So if this was the initial point where it was acting, it has moved downward distance d. So what are the things we indicated here? We indicated direction which the force is acting. We also indicated direction of displacement. And all we need to do now, so now the calculation of work done, what would tension be? We have already done in terms of loss of motion. Tension will be equal to m times g plus E naught here. E naught here is minus g by 3 downwards. So this force will become equal to 2 by 3 mg. So tension is 2 by 3 mg. Displacement is d. Angle between them is 180. So this into cos of 180. That's the expression. And we can easily calculate. So they are very simple. This is just to start, make up some of you, those who do not recall work done well. This is simplest way you try and understand, and then slowly you can gain speed. Let's look at second question. Small block of mass m. Now again we are in the lift, but now floor is not horizontal. There's an inclined rough wedge of inclination theta with the horizontal. So this is an elevator here. In elevator we have kept a wedge here which makes an angle theta, and this is a rough wedge. So we have placed a block m here, and elevator goes up with the uniform velocity v. So moment you notice uniform velocity means that there's no acceleration. It is less like a object placed on an inclined plane. So forces would acting in case of constant velocity would be same as the forces which would have acted if it was in a state of rest. So it does not slide, it goes up like this. So this is my initial state and it has moved here. So what is displacement from here to here? This is the displacement. So displacement is easy. Now let's see what we have to calculate here. What is work done by frictional force? We have to calculate separately. We have to calculate work done by normal force separately. So this is the two independent. We don't have to calculate work done by all forces. Of course, if we have to calculate work done by all forces on this block M, work done by all forces on what? This small block which is placed on the inclined plane. Since it is moving the constant speed, work done by all forces, of course, has to be zero. But here we have to calculate by individual forces. So let's understand here what we are going to do. We are going to mark displacement. We are going to mark forces with direction. Which are the forces we are concerned here? Again, let's mark those forces here. So this block, which direction the friction force will act? We understand from here, this in a state of rest, we resolve. So this, whenever inclined plane, we take this x-axis in normal direction, either n cap or y-axis. So we can easily arrive at n is mg cos theta, and friction force is static state. Friction force will be equal and opposite to other force, so that net acceleration along the slope is zero. Friction is mg sin theta. And what is this direction? This angle will be theta, and this angle will be theta. All we need to know now, if I have to calculate work done by friction force, I know the magnitude, I know the displacement. In time t, displacement is vt. This is direction displacement. Both vectors are tail to tail. So I need to either I take cos theta, or I can take, this is displacement. Let me take component of friction along the direction of displacement. So component of friction force along the direction of displacement will be equal to F into sin theta. So that's work done by friction is vertical component of F into displacement. Why vertical component? Because displacement in the vertical direction. So force is mg sin theta, is component because n sine theta into vt. That's the work done by friction. We have to work done by normal reaction here. Again, we take its component. Now its component will be equal to mg cos theta is the force. Its component becomes e2 cos theta into vt. That's the work done by normal reaction. So what is interesting, we notice what is the work done by friction plus normal reaction both put together. If we add it up, what are we getting here? In that case, we add work done by both is equal to mgvt. And if we calculate what is the work done by gravity here, work done will be equal to minus mgvt. So if we add all the forces, it has to come to zero, and it does come to zero. So if same question, if I ask you in a different way, if I gave what is the work done by the contact force? What is work done by the contact force? So in this case, work done by contact force very easily could have worked out, because work contact force has to be equal and opposite to gravitational force. So work, if gravitational force is mg downward, resultant contact force acting on the block is in the vertical direction. If you take vector sum of these two, what has to be vector sum? Vector sum of normal reaction friction force has to be equal to mg. The work done by contact force here in this case is mg vt. Okay. And some of the questions which have come, typically we haven't seen too many difficult questions on this topic. The questions have been easy to medium level only, and that's what initially we need to focus on. This is also one of the questions which have come in mains. A block of mass m is kept on a platform which starts from rest with constant acceleration of g/2 upwards, shown in the figure. What is work done by the normal reaction in the block in time t? You notice this question also very similar to previous question. Previous question, acceleration was zero. Now there's an acceleration. If I mentally draw a figure here, this is what the figure would look like. Initially, it starts with zero velocity. But this whole thing, this platform has an acceleration g/2. So this block also will get accelerated by g/2. And we need to calculate in time t. So again, we'll go to the same thing, mark the force and mark the displacement and find the angle. Displacement is pretty simple. Displacement is equal to 1/2 at square, which becomes g/4 t square. This is a displacement, vertically upward direction. We have to calculate work done by normal reaction. Let's mark the direction normal reaction is upwards direction. And what is the normal reaction here? Normal reaction will be equal to, again, mg plus a naught, which will be equal to 3/2 mg. And both are in the same direction. Theta is zero. So what is work done? Pretty simple. This term into this term is equal to work done. And you notice so simple question it was. Okay, so that's the displacement and this work done. Let's continue with some more. So can there be something tricky as well? Yes. Okay, it could be a little tricky as well. Okay, I think some question I missed here. This was a question here. If the force acting here is like this, what is force here? This is the force acting. And but this is moment I see, this is a variable force here. It acts on a particle moving in xy plane, is starting from origin. The particle is taken along positive x-axis. So particle is taken from here to A to point AO, and then parallel to y-axis to AA. So this is, it has undergoes two states of displacement. One is from O to A, and then A to B. And now it is a variable force here. What is the work done by force F on the particle? Okay, so that's what we need to calculate. And I think I missed that mark in the question previous slide. I'll go back and see, recall this question here. So that's what the force is, and we need to calculate work done. How would I calculate work done here? I'll calculate work done in two parts, O to A and A to B. And in this case, it becomes a little slightly different. Let's understand how do we calculate this. Work done by variable force, this is what we need to, again, I mentioned here. That's what we need to remember. Work done by variable force is like this. We need to integrate if force is not constant. So in this case, the whole thing I could have written is fx into dx, x1 to xy, plus, see, when I take a dot product here, it becomes fx into dx. What are the limits in that case? In that case, we will take the limits also corresponding to x. It will be xi to xi. Similar way, there will be terms for y also and z also. That's written a summation sign. So this is how we calculate work done by a variable force. Looks a little scary, but it is not so much. Let's do it for the first part, from O to A. O to A, what will be work done along the path? So this particular path here, in this particular case, what we notice, two things we notice. Along this path, y always remains 0 and dy is equal to 0. If dy is 0, work done will only contain x component, fx into dx. Because y of dy is not coming, dy is 0, dz is equal to 0. So it will be x component, which was minus ky in that question. I think I've just missed that question writing here. So we write only x component, which is minus ky into dx. That's the expression. But from where to where, limits is from which x to x is equal to 0 to x is equal to a. But here y is equal to 0, the whole term work done becomes 0. So as it moves from O to A, work done is 0. Let's do the second part. As it moves from A to B, the y component. Now in this case, dx is equal to 0. Since dx is 0 and dz 0, it will only have dy into fy. Fy into dy. Fy was given as minus kx into dy. In this case, x is a constant. X is a constant here. What is x equal to? X is equal to a, so it is equal to minus ka into dy, and minus k into dy. So it becomes equal to minus k square. That's work done. Now this is simple question. Now let's do the second part also. So we are done around two parts. Suppose you take the second part. Let's understand what happens if path is defined. What will be work done if particle is taken directly from origin to point AA? Is taken directly from origin to AA. Okay. What is the path in that case? If this is a path here, can we define the path in terms of mathematical relationship? It is directly taken, is taken along the straight line. So I can define path in terms of equation of the line. That becomes my path. So whenever path is defined, it gives a relationship between how x and y coordinates are related and how they will change. If y is equal to x here, dy is equal to dx. So this is something, moment path is defined, we can use this relationship also. Now let's write the expression here. So in this case, if this was the force here, what is the work done here? We take fx into dx, fx is equal to minus ky into dx, x we are varying from 0 to a. Similarly, we'll take y component of force into dy, which is minus ky into dy, and y also varying from 0 to a. This expression, but this expression I cannot directly integrate because here this variable is x, and I have to write x, y also in terms of x. But since the path is given, in place of y, we can substitute x here, and in place of x, we can substitute y here, and it can easily be integrated. So I hope you understood. Whenever path is given, using the path means equation between x and y. So whenever xy relationship is given, so whenever we integrate, so depending on which part, we substitute either y in terms of x or x in terms of y and integrate and get an option. If we write this one, now it becomes very easy here. It becomes equal to its integration minus kx square by 2. We substitute, it becomes minus k square by 2. And both of them we add up, it is minus ka square. which is same as work done along this path is same as work done along this path plus this path. So this force here, what is given here, appears to be a conservative force. Right, next come to next one. Now looks a little more scary. So what is given here? What is work done on a particle of mass m by a force? What is this force here? This force is, it depends on x coordinate as well as y coordinate. Or in short, this force is a function of position, which point it is acting. K is a constant. So when the particle is taken, so this is a force here. Now let's understand what is the particle and what is the displacement. Particle is taken from point A0. This was the initial point, A0. And to another point 0A, it is taken to this point, and even path also is defined because this is here force is varying with position along a circular path. So this is the displacement, this is the path which has been taken, and we need to calculate what is the work done. Okay, so how do we calculate work done in such case? In this case, moment the path is circular here. See, we should try and express this force in terms of radial component and tangential component. Then only calculation of work done becomes simple. Otherwise, it becomes too complicated. So how do we convert? And when we talk about radial component and tangential component, actually we are talking more in terms of polar coordinate. So let's take, if the general point P, if I take, let's try and understand how do we convert. This point P has a coordinate x and y. This is in terms of our normal Cartesian system. But you have to write in polar coordinate. This point P will have some distance r from the origin, r, and it will make an angle theta. And when we take polar coordinate, see, when we talk about angle, angle is always measured with reference to a particular line. So which line we have taken here? We have taken the reference line to be positive x-axis and anti-clockwise direction as positive. That's a normal convention unless we mention otherwise. So if I do so, I can convert this to whatever there's, even the force also and other things also in terms of polar coordinate. So let's see. And this question, what we are going to do now, it is applicable in several cases. So pay attention, see that this is understood. And this is nothing very complicated, fairly simple. Let's see that how do we convert. Any such thing is given. So path is circular, we convert into polar coordinates. So let's first understand what this magnitude of force is. So magnitude of force, denominator is constant. So if I take this square plus this square, whole thing is square root. So what will happen? Numerator also become root of x square plus y square. Essentially, it will come to k divided by root of x square plus y square. And if I convert it to polar coordinate, it becomes k by r square. Now this gives me better clarity. What I understood now, okay, the force is inversely proportional to square of distance from the origin. I understood its magnitude in terms of its distance from the origin, but still the direction is not clear. Now let's move on to direction part here. Okay, so I hope this part is clear. We calculated, and then see, once you understand one question, I think you'll find whenever we come across such question, we should be easily able to solve it. So when we talk about direction in terms of circular motion, rather than take xy coordinate, we take tangential and radial direction. So let's say if this is, if I define, this is a direction r cap. What is this r cap? This direction is angle positive theta with x positive x-axis as reference. So what is the unit vector which makes angle theta? So unit vector, basically what will, I'll divide this vector by its magnitude, and the unit vector very easily. So if I take magnitude as 1, x component becomes cos theta, y component becomes sin theta. So this is unit vector making an angle theta in anti-clockwise direction with x-axis, which I find useful anyway and very simple to understand. Just take the magnitude as 1, x component, y component. So r vector is cos theta I cap plus sin theta j cap. Right. But I'm interested in one more thing. I'm interested in tangential vector also. Which tangential? There are two directions possible. I could have taken one more in the anti-clockwise direction, or I could have taken one in the clockwise direction. I have taken one more, which is further from r vector. It is further rotated by angle pi by 2 in anti-clockwise direction. How do I find this vector? So if I take this t cap vector, it makes an angle of theta plus pi by 2 from x-axis. This angle is pi by 2 plus theta. So again, to find this unit vector in place of theta, I'll substitute pi by 2 plus theta. So sorry, the unit vector in the tangential direction, t cap, is equal to cos 90 plus theta. 90 plus theta becomes minus sin theta I cap, and this becomes cos theta j cap. So this is a unit vector, and anyway you could have calculated if we take unit as 1, magnitude as 1, and if this angle is theta, this angle becomes theta. Is x component, I component becomes negative, y component becomes positive. So this is a unit vector, tangential unit vector. So can I convert in terms of xy coordinate? Can I write this angles in terms of xy coordinate? What is cos theta? Cos theta, if I take a form complete a right angle triangle, what is cos theta equal to? X coordinate divided by the distance. So cos theta is x by root of x square plus y square, and sin theta is y by root of x square plus y square. So now with this, can I write this whole expression in terms of r and theta? That's what our aim is. Write this expression in terms of r and theta. So what I notice, there's a term x divided by root of x square plus y square. If I separate x square plus y square, split this term into two. This term which is written as x by this power of 3 by 2, I can write something like this: power of 1 into power of 1 by 2. This is what its expression is. Now, this is the expression is. What is this term? This term is equal to r square. And what is this term equal to? This term is nothing but cos theta. Okay, so this term is cos theta. So write this force here. I take this r square common. So force becomes k by r square cos theta I cap plus sin theta j cap. That's the force. If there's a force, what we understand, which direction is the force acting? This force here from this direction, this force is acting at angle theta with the x-axis when particle is at particular point here. So the force is inversely proportional to square of distance from the origin. It acts in the radial direction always. So wherever the point is, always direction of force is radial. If the direction of force is radial, if I move the particle along the circular path, work done will be 0 here. So in this particular case, the work done comes to 0. We can take one more radiation, but what was more important? More important was to understand how to convert something which is given in this form into polar coordinate. What is the polar coordinate? Well, two things we use. R square is equal to root x square plus y square. And this is the direction of tangential direction and radial direction. And we can write this term as cos theta and sin theta. So another variation of the question could be, see what, rather than having this force, if I change the force to something like this. When I write this force here, what is this force here? Which direction is this force acting? This force is acting in the radial direction. Can you easily spot which direction is this force acting now? This force, if I write this force here, this force will become equal to, if I take x square plus y square as common out, it becomes equal to x square plus y square, and it becomes equal to minus y by root of x square plus y square I cap plus, sorry, this term has to be, I missed something here. It should be x plus x divided by root of x square plus y square j cap. So what is this term equal to? This term is sin theta, this term is cos theta. So this term becomes equal to, when I write this, if a force is given like this, I make a small correction here. This is not y, this is x. So this force becomes equal to 1 by r square minus sin theta I cap plus cos theta j cap. So which direction the force is acting? This force is always acting in the tangential direction. So if this force acts on this particle here, the magnitude of force becomes equal to 1 by a square, and is always acting in the tangential direction. The work done by this force will be equal to magnitude of force into pi r by 2, path length. Everywhere this force will be tangential, and magnitude of the force is equal to 1 by a square and into pi a by 2. That was the work done by this force here. Okay. If it is understood, I hope all of you understood. I'll move on from here. Okay, next question again of a variable force. So rubber band of this rubber band of negligible length is something like a spring only. Stressed by a distance x, it exerts a restoring force of magnitude like this. So in this case also, what is given here? Fx is equal to, that's a F force is a function of its displacement of one end. Only thing what is different here, so this force here is not proportional to x like a spring. Okay, and this is exerted force of magnitude. And A and B constant. What is work done in stretching the unstretched rubber by a length L? Okay, so conceptually, how do we solve this question here? It's a variable force. Let's try and visualize what is happening here. And in a way, there's some similarity to what happens in case of a spring. So here, rather than stretching, see, when we stretch here, if we take a piece of rubber, initially it is very small length. We start applying a force. As we keep gradually increasing the force, its length also will keep on increasing. So every small element, when we stretch, the force will keep increasing, force will keep varying here. Since the force is constantly varying, to calculate work done, we need to think in terms of several infinite small stretches. And for each small stretch, force can be treated as constant, and then you can calculate work done. So conceptually, we divide the whole stretch from 0 to L into infinite number of small stretches, something like this. In this case, what does this figure show? Initially, this length was almost 0. In this case, what has happened? It is here stretching it from length x to x plus dx. So what is the extent of this stretch here? Beginning with x, ending with x plus dx. This means stretch is dx. So let's calculate work done for this small stretch. So once we calculate here, similar way we can add work done for all small stretches by process of integration, because work done is a scalar quantity. So we have work done for a random small stretch. And since it is one direction motion, say everything is in terms of 1D, we take random stretch, we do in several other cases from a random value, random position x to x plus dx. What is the work done here? By external force. See, this rubber band will exert a force in this direction, but external force has to be in this direction. External force has to be in the positive direction. So we write fx is equal to ax bx square into dx. That's the work done for the small stretch. What is the total work done as the length, as the x changes from 0 to L? Sum of the work done. So that becomes my sum of the work done from stretching from 0 to L. Had the question been from L by 2 to L, accordingly my limits will change. And a very easy integration we can find. Okay, next question is something like this. So we are just doing work done, nothing new. So in terms of just fx into dx, or if it is multiple dimension, each direction. Let's say block of mass m is initially at x is equal to 0, is acted upon by horizontal force at x given by this. So what is the force here? The force which is acting on this particle is not a constant force. It's a position dependent force. It depends on its position. So it's varying force, varying with position. There may be some forces vary with time. We'll see that later. And what is given here? See, so what is this force? As at where is this force maximum? If I take only positive axis, this point as x is equal to 0. See, this force is initially it is maximum. It keeps on reducing as x increases, and maximum value of force is a. So initially, when the object was at the x is equal to 0, force acting was a. This object would have started its motion only if this force was greater than maximum friction force. That's why A must be greater than mu mg. Then only motion will start, otherwise motion would not have started. Coefficient friction is given as mu. What is the work done by 0? So what is the distance the block travels so that work done not becomes 0? Okay, work done one in starting from x equal to 0. What is the value of x so that work done becomes 0? Same question could have been worded. After what distance this block comes to stop? Why it will come to stop? It started with 0 velocity. If over a distance x, net work done is 0, it means change in velocity is 0. Which means initial velocity is 0, final velocity also will become 0. So same question can be worded in a different way. Now what is distance x over which work done is 0? Okay, at the distance traveled with x, what is work done? Two forces. This force is doing work and friction force also is doing work. This force is variable force, friction force is a constant force, and friction force is equal to mu mg here. So we write both the forces. Work done by this varying force is 0 to x. value of fx into dx, similar to what you have done here. Fx into dx, initial position, final position, minus mu. Why is minus here? Displacement is towards right and friction force toward left. Angle between the force and displacement is 180. So we equate this term whole to 0 and we'll get our answer. That is fairly simple question, and that's the value of x we get. Okay, next question. A bullet of mass of 10 gram is fired horizontally with the velocity of 100 meter per second from a rifle situated at height of 50 meter above the ground. If the bullet reaches the ground with a velocity of 500 meter per second, it has lost some velocity. What is the work done against air resistance? This is a question given G is equal to 10. Okay. So now onwards, I'll give you. Okay. So first thought, whenever I see question like this, work done, what should come to your mind? Work energy theorem. Work energy theorem is always valid. So what is change in kinetic energy is work done by all forces. What are the forces present here? That is not too difficult to identify. Work done by air resistance plus work done by gravity. Let's substitute. That's all. But now that's all is pretty simple. What is change in kinetic energy? Change in kinetic energy, final kinetic energy minus initial kinetic energy, which is equal to 1 by 2 m Vf square minus V square, and well, direction is immaterial here, is a scalar quantity. That's what he had done. So 1 by 2 mass, final velocity is 500 meters square, for 500, and initial velocity is 1000. So it is losing kinetic energy. Whatever, we just substitute this sign, is equal to work done by air resistance plus work done by gravity. So it is something like this. What is the work done by gravity? Work done by gravity, I will take work done by gravity is equal to gravitational force, which is mg acting downwards, m into g, into component of displacement in the direction of force. Which component? Vertical component. I don't know, but it doesn't matter what path it takes. Only matter is what is, if this is a displacement like this, what is the vertical component? Vertical component also very easily given, which is 50 meters. So when I substitute this value, this is a term which you can work done by air resistance, and we get my answer. So this also is a simple example of work energy theorem and its application. Only thing later on what we see here, whenever some cases we want to make use of potential energy, we'll make some slight change. Work done by non-conservative force becomes equal to change in kinetic energy plus change in potential energy. Okay, let me do one small thing. This is something it may come in different forms. I'll just doing in a general way. Let's say body of mass m is slowly hauled up the hill. And here the slope is not constant, it is varying slope. This is something like this again. You're back to Ocean Park. And like Ocean Park, no, but this time you're not sliding down, which is fun. You're pushing mass up, which may not be fun. So there's a force F. So there's a body of mass m is slowly hauled up the hill, something similar to that, by a force of constant magnitude. So the force is always constant in magnitude, but direction is along the tangent. So it is direction is along the tangent. So whichever shape, as the shape, the direction keeps changing depending on how the slope is changing. So it moves from lowest point to, it has mass is moved from here to here. Okay. And is slowly hauled up. Slowly means whenever you come across word slowly, what we need to understand here, slowly means at this point also velocity is very small. And this point also, so this, I hope this part is clear. This is the initial point and this is the final point. And whenever word slowly is mentioned, there's no change in kinetic energy. So work done by all forces put together is equal to 0. So what are the forces? If we had to write that one, the first thing we understood, the net work done is work done by all forces equal to 0. So work done by F plus work done by friction plus work done by gravity, all put together is equal to 0. But it's a little difficult to calculate what will be the work done by friction. So let's see that one, what happens in case of friction. Let's take a common case. Rather than taking all this long path, let me take a small element of the path. If I take a small element, displacement along the slope is dl. This angle is theta. If angle is theta, friction force will equal to mu mg cos theta, mu times n. Now this is something kinetic friction. Kinetic friction will be equal to mu times normal reaction. Only assumption what I'm making here, see when kinetic, see normal reaction is equal to mg cos theta only if the acceleration in the normal direction is 0. So here the path is curved. You know, in case of curve, there could be centripetal acceleration, but centripetal acceleration is v square by radius of curvature. So since the velocity is small, even for curved path also, normal acceleration is 0. That's why the friction force will always equal to mu mg cos theta. So let's do for a small element, and let's see this something important we can understand from here. What is what important we understand here? Work done by gravity and friction here. What will be work done by gravity in this case? Work done by gravity, I will take gravity will be equal to component of displacement into mg. Component of displacement is opposite direction. The work done by gravity will be equal to mg into dh. Dh is the vertical component. What is dh be equal to? So I can write work done is equal to minus mg into dh, which is equal to, which is nothing but projection of displacement on a vertical direction. This is work done by gravity. What will be the work done by friction? Work done by friction will be equal to magnitude of friction into dl. Angle between them is 180 to minus this term. Okay. So what I do here, if I look at the term dl cos theta, these two terms, what is dl into cos theta? Dl in cos theta is nothing but dx here. So this term becomes equal to mu ng into dx, provided an is equal to 0. That's the only assumption here. So what we find here, as we move, the work done by gravity is equal to mg into vertical displacement, negative, and work done by friction is equal to mu mg into horizontal component. If I apply this logic, as it moves from here to here, work done by friction will be equal to mu mg into L, and work done by gravity will be equal to mg into minus h. That's what it is. So just projection. Okay, it doesn't matter what the shape is. This becomes independent of theta. It becomes just a projection. So that's a okay. So that's what last thing I'll do here. So I'll stop here and we continue from here in the next session post lunch.